It was the coldest morning in the history of the Florida Space Coast. Tuesday, January 28, 1986. The temperature had plunged overnight, dropping to 18 degrees Fahrenheit. That is minus 8 degrees Celsius. For a spacecraft designed to kiss the edge of absolute zero in the vacuum of space, a little frost on the ground shouldn't matter. That is what the public thought. That is what the news anchors said. That is what the families sitting in the VIP stands believed as they huddled in their coats, watching the launch pad 3 miles away. But inside the Launch Control Center, and deep inside the offices of the engineers who built this machine, there was a different feeling. It was not excitement. It was fear. A specific, paralyzed kind of fear. They knew something the world didn't. They knew that the monster sitting on the pad was allergic to the cold. The Space Shuttle Challenger wasn't just a vehicle. It was a promise. It was the Teacher in Space mission. Krista McAuliffe was going to teach a lesson from orbit. The eyes of the entire world, including millions of school children, were fixed on that launch pad. The pressure to launch was heavier than gravity itself. At 11:38 a.m., the engines ignited. A roar that shook the earth, a pillar of fire. It looked perfect. The crowd cheered. The capsule communicator spoke the famous words. "Challenger, go at throttle up." Commander Dick Scobie replied.
"Roger, roll, Challenger."
And then, silence. 73 seconds. That is all it took to turn a triumph of engineering into a scar on the human soul. But here is the haunting truth. The failure didn't happen in the sky. It didn't happen at 46,000 feet. The failure happened days before. It happened in a meeting room. It happened in the chemistry of a simple rubber ring, no thicker than a pencil. Let's decode this, step by step. You are watching Matverse. Today, we unlock another secret of the universe. Let's begin. To understand why Challenger fell, we first have to understand how it flew. The Space Shuttle was the most complex machine ever built by human hands. It had over 2.5 million moving parts. If just one of those parts fails, the consequences can be catastrophic. But today, we are focusing on the muscle of the system, the solid rocket boosters. These 2 white towers on the side of the shuttle are not like normal engines. They are essentially giant Roman candles. Once you light them, you cannot turn them off. They burn until they are empty. They provide 80% of the thrust needed to get off the ground. But here is the catch. These boosters are huge. They stand 149 feet tall. They were too big to be shipped across the country in one piece. So they were built in segments. 4 massive steel segments, stacked on top of each other. Where these segments meet, you have a joint. This joint is the Achilles heel of the entire system. When the rocket ignites, the pressure inside jumps to nearly 1,000 pounds per square inch in milliseconds. The steel casing actually balloons outward. It expands. This expansion creates a tiny gap between the metal parts. To stop the burning hot gas, which is hotter than the melting point of steel, from escaping through that gap, engineers used rubber seals. These are the O-rings, 2 circles of synthetic rubber. Their job is simple. When the gap opens, they need to pop into the space and seal it shut, like a cork in a bottle. But on the morning of January 28th, physics was fighting against them. Rubber is a polymer. It is made of long chains of molecules that love to tangle and stretch. That is what makes it bouncy. But this bounciness, what engineers call resilience, is entirely dependent on temperature. Think of a piece of chewing gum. On a hot summer day, it is soft, sticky, and stretches easily. But if you put that gum in the freezer, it becomes hard, brittle. If you try to stretch it, it snaps. The O-rings on Challenger were made of a material called Viton. It was a high-grade rubber, but it had a critical weakness. At 32 degrees Fahrenheit, it began to lose its elasticity. At 28 degrees, the temperature on the launch pad that morning, it was no longer acting like rubber. It was acting like hard plastic. Here is the nightmare scenario. When the booster ignited, the steel casing expanded. The gap opened. Normally, the O-ring would spring forward in a fraction of a second to close that gap. But on this morning, The O-ring was frozen stiff. It moved too slowly. It was milliseconds too late. And in rocket science, a millisecond is the difference between life and death. Now, you might be asking, didn't they know? Yes, they knew. The night before the launch, there was a teleconference, a meeting that has gone down in history as one of the darker moments of engineering ethics. The engineers at Morton Thiokol, the company that built the boosters, were panicked. They looked at the weather forecast. They saw the ice. They looked at their data from previous flights. They saw a pattern. The colder the launch, the more damage the O-rings took. Roger Boisjoli, a top engineer, fought hard. He told NASA, "Do not launch. It is too cold. We have zero data for these temperatures." He was basically screaming into the void. He argued that launching below 53 degrees was a roll of the dice. But NASA was under pressure. The program was falling behind schedule. The news media was mocking them for delays. The president was preparing the State of the Union address and wanted to mention the teacher in space. NASA managers responded with a sentence that chills the blood. One manager turned to the engineers and said, "My God, Thiokol, when do you want me to launch? Next April?" Under immense pressure, the Thiokol management overruled their own engineers. They signed the paper. They gave the go. Roger Boisjoli went home that night and told his wife, "I think we are going to kill the crew tomorrow." The sun rose on January 28th. The launch pad was covered in icicles. Some were feet long. The ice team was sent out to inspect the shuttle. They measured the temperature on the right solid rocket booster. It was 28 degrees. At T-0, ignition. If you look closely at the archival footage, right at the base of the right booster, you see it, a puff of black smoke. That was the O-ring failing. It vaporized. The seal was broken. Hot gas, burning at 5,000 degrees, started to eat past the barrier. But then, a strange miracle happened. A piece of solid fuel slag, essentially aluminum oxide ash, plugged the hole. It temporarily sealed the leak. For nearly a minute, Challenger was flying on luck. The crew was alive. The mission was proceeding. They passed through Max Q, the point of maximum aerodynamic pressure. The shuttle was shaking violently. Then, at 58 seconds into the flight, Challenger was hit by the strongest wind shear ever recorded during a launch. The shuttle was buffeted sideways. This vibration was too much. The temporary seal made of ash shattered. The flame returned, a concentrated jet of fire. And it was pointing directly at the strut, the metal bar holding the booster to the massive orange fuel tank. Imagine a blowtorch cutting through a support beam. At 72 seconds, the strut gave way. The bottom of the booster swung free. It rotated. The nose of the booster smashed into the top of the fuel tank. This is a common misconception. Challenger did not explode in the nuclear sense. It disintegrated. The aerodynamic forces tore it apart. The fuel tank collapsed, releasing all its hydrogen and oxygen at once, creating that massive fireball. But the orbiter, the plane with the crew inside, was ripped free. This is the hardest part of the story to tell. For years, NASA let the world believe the crew died instantly in the explosion, that they felt no pain, that the decompression knocked them out immediately. But when they recovered the wreckage from the ocean floor, months later, they found evidence that tells a different story. The crew cabin was built extremely strong. It survived the breakup intact. It continued to fly upward on its own momentum, reaching 65,000 feet before arching over and falling back to Earth. Investigators found that 3 of the personal egress air packs, emergency oxygen supplies, had been activated manually. One of them belonged to pilot Mike Smith, but the activation switch was behind his seat. He couldn't have reached it. That means Judy Resnick or Ellison Onizuka reached over and turned it on for him. This tells us they were alive. They were conscious. They were trying to save each other, even as they fell. The fall lasted 2 minutes and 45 seconds. We do not know if the cabin depressurized. We hope they lost consciousness from lack of air, but we will never know for sure what was said or felt in those final minutes before they hit the water. It is a reminder of the immense bravery of those 7 souls. 7 souls. They were professionals until the very end. The fall lasted 2 minutes and 45 seconds. We do not know if the cabin depressurized. We will never know for sure what was said or felt in those final minutes before they hit the water. It is a reminder of the immense bravery of those 7 souls. They were professionals until the very end. After the disaster, a commission was formed to find the cause. It included Neil Armstrong and a physicist named Richard Feynman. Feynman was a Nobel Prize winner, a genius, and a man who didn't care about politics. He sensed that NASA was trying to hide the simple truth behind complex charts and data. He wanted to cut through the noise. On live television, Feynman performed a simple experiment. He took a piece of the O-ring material, clamped it tight, and dropped it into a glass of ice water. He waited a few minutes, then he pulled it out and unclamped it. The rubber didn't bounce back. It stayed squashed. It had the indentation of the clamp. He looked at the cameras and said, "I believe that has some significance for our problem." In that one moment, he exposed the failure. It wasn't magic. It wasn't an act of God. It was physics. Rubber gets hard when it's cold, and NASA launched anyway. Feynman later wrote in his report a line that should be etched in every engineering school in the world. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. It has been 40 years. The scars of Challenger are still visible in the way we explore space today. The shuttle was grounded for years. The design was changed. The management culture was overhauled. But the lesson remains. When we push the boundaries of what is possible, we walk a razor's edge. Francis Scobie, Michael Smith, Ronald McNair, Ellison Onizuka, Judith Resnick, Gregory Jarvis, Krista McAuliffe. They were not just victims of a tragedy. They were pioneers. They accepted the risk because they believed in the future. They believed that reaching for the stars was worth the cost. We study their loss not to assign blame, but to ensure that their sacrifice was not in vain. To remind ourselves that in the face of the cold, unyielding laws of physics, we must be humble, we must be honest, and we must never forget the cost of the journey. This is Matverse, and today we unlocked another cosmic secret. Please subscribe to the channel or follow the page. I'll see you in the next video, where we'll explore even more.